Hello, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KEE 301. So we are in the unit 5 where we have started about some basics of Faraday's law in the context of waves and its applications. So next topic, that is displacement current. So as I said previously about the displacement current, so this concept occurs when we have the time varying field, right? So, and this displacement current is also responsible for the wave transportation from one point to another point. So we will come up to the point where we can decide what is the displacement current and what is the displacement current density. So previously we are aware about the static magnetic field relation in the Maxwell's equation, where it says that del cross H is equal to J. Okay, so J is nothing but this is the conduction current density and H is magnetic field intensity. So let's have one look into it when we take the divergence of this equation. So just take the divergence of this equation. Let's see what will happen. Then this is del dot del cross of H in the left hand side, and the right hand side it will become the del dot J. Okay, and in this we know the identity about that the divergence of the curl of any vectors is equal to 0. We know the identity. What is that? That we know that the divergence of curl of any vector, and this is equivalent to 0. So in representation, that is divergence curl of any vector, if I am saying the vector is A, okay, is equal to 0. And A is what? This is magnetic vector potential, right? So the curl divergence of curl of any vector is 0. So it means that here in place of A, if we have this vector H here, then divergence of del cross H, this is must be equal to 0. So here and we have also discussed in the last few lectures before about the continuity equation. So what this continuity equation says, that where the del dot J, or the divergence of the J, is equivalent to the minus del rho v upon del T. So we know about this equation and it follows the equation by the continuity equation. So but if by this equation we see that del dot J is equal to 0, but actually del dot J is equal to minus del rho v upon del T. So at what condition this is 0? So this will be 0 when we have the constant rho v, or we are charge free region, right? So if there is a charge free region, so in this case there is no impurity can be included into the substrate, right? So it cannot be 0. So it means this equation is when it is 0, it means this is compatible with the time invariant case. When we have time varying field, so in this case, in the time varying field, in this condition, this cannot be 0, right? So what is the change we may make? So in this equation, what we are doing, we are simply adding one component, that is the JD here. So we can see we have just added del cross H is equal to J plus JD. In that JD is what? This is the this is defined as the displacement current density. So J, this is the conduction current density, okay, and here JD, this is the displacement current density, okay. So now again we will take the divergence of this equation. So divergence of this equation, which I said this is equal to 0, and the equation will become del dot J plus del dot D, okay. So when you take the divergence of this equation, so this left hand side will become like this. When we take the divergence of this equation, so in this case we will use the distributive property. So it will become the del dot J plus del dot JD, right? And that is equal to 0. So in this, what we can do, we can take this portion the left hand side. So it will become the del dot JD is equal to minus del J. And what is the del dot J in terms of the in terms of continuity equation? So in the previous equation, we have seen that del dot J is equal to minus del rho V upon del T. So simply we can put the minus with the minus sign del rho V upon del T. So minus minus will become plus. So it will become the del rho V upon del T. Now we know about the next Maxwell's equation. What is that? About this one, we know the Maxwell's equation is del dot D is equal to rho V. So in place of rho V, we can put the del dot D. So here we have put it. We have put here that del dot D, which is of del upon del T. So just take this one inside. So it will become the del dot del D upon del T. So simply now compare this equation with this one. So what we will get? We will get the JD is equal to del D upon del T, right? So this JD is equal to del D upon del T. So this is equivalent to this one. Okay. So this is the displacement current density, which is equivalent to del D upon del T. So now, as we know, the previous equation was del dot H is equal to J, and now we have added the second component, that is a JD. So in this case, JD, in place of JD, we can put the del D upon del T. So now the next Maxwell equation, or the modified Maxwell's equation, is del cross H is equal to J plus del D upon del T. So this is the modified Ampere's circuital law, or the Ampere's circuital law in the time varying B field. Okay, time varying field. So in that, JD is del D upon del T is also known as the displacement current density, and J is the conduction current density. So this is density. I hope this point is clear. So this is the another this is the one more Maxwell's equation in the time varying B field. So we can recall all these things with some more intuition about displacement current density, where Ampere's circuital law, based on Ampere's circuital law in differential form, this equation will be del cross H is equal to J plus del D upon del T, and we can convert it in terms of the integral form. So in that, the equation will become, when we take the integration of this equation, it will become with the surface, open surface. So it will be the del cross H with the open surface is equal to surface for this case, and the for second term of this equation. Okay, so now because we know this equation, this is the open surface, so here we can apply the Stokes theorem. So we can apply the Stokes theorem in this left hand side. So when we apply the Stokes theorem, what we will have? So what is that? Let's apply. So we have del cross H into ds open surface is equal to closed path H dot dl. Okay, so it will become the H dot dl. So in place of this left hand side, we can input this value, this expression H dot dl, and J dot ds. So this term is nothing but this is the, because J is the conduction current. So conduction current density through the given surface area will give the conduction current. So this is the IC, and this is del D upon del T dot ds. So this is nothing but this is a displacement current. Okay, so the second term has the unit of current because it is proportional to the time derivative of the flux density D, which is called the electric displacement. So this portion is called the electric displacement. So this term is therefore called a displacement current ID. So these expressions are very, very important. So for numerical point of view, the 2 mark question can come in your exam based on the displacement current or the displacement current or conduction current density. So IC is nothing but J dot ds, and ID is equal to JD dot ds, and in place of JD we can put the del D upon del T dot ds. Okay, so this equation will come in this way, that H dot dl is equal to IC plus ID is equal to I. So this I is a total current enclosed, and this is equal to IC plus ID. So this is the total current into the system. So in electrostatic, which we are very much aware about, that the del D upon del T is 0, because this is in electrostatic. What will happen? This is the there is no motion of charges, static field is there, this time invariant case. So in that time invariant, del D upon del T will be 0. So here the ID will become 0, so I will be equal to IC only. So the concept of displacement current, which was introduced by the James Clerk Maxwell when he formulated the unified theory of electricity and magnetism under the time varying conditions. So here let's have the feel of this by using the two parallel capacitors. So in which the displacement current concept come into the picture, where when we connect these two sources, these plates 1, plate 2, and this is connected with the voltage source, so the current which is flowing into it, I1, and which is passing through the imaginary surface S1. So let's find IC and ID through each of the two imaginary surfaces and cross section of the conducting wire S1 and S2. So in this, here this equation will become that E is equal to AY VC upon VD. So here VC, we can put the VC is equal to the V0 cos omega t. Okay, so here we can see. So in place of VC, we can find this value. So this is another imaginary surface. So in that, this equation will become the, let's say, VS, that is equal to V0 cos omega t. This is the example which we are taking care of. So in that, the perfect conducting wire, electric field and electric flux density is always be 0, as we have discussed about the properties of the conductor. Within the conductor, electric field is 0. Okay, so in that the ID will be also 0, and IC1, we can find this one through this equation, that I1C is equal to C dV upon dt. So this equation is very well known to us, and we, in place of VC, we can put the V0 cos omega t. So when we differentiate it, then the value which we are getting minus C V0 omega sin omega t. So with no displacement current in the wire, the total current in the wire will become I is equal to IC. Okay, because there is no, we are not considering the case for the perfect conducting, in which the displacement current is 0 in between the plates of the conducting plates. Then what will happen? Only the conducting current will be present. So here it will be I will be equal to the IC, and that expression is minus C V0 omega sin omega t. Now in perfect dielectric case, so in perfect dielectric case with the permittivity of epsilon between the capacitor plates, so sigma will be 0. Okay, so there are two extreme cases. First is the perfect conducting plate, perfect conductors, and second is a perfect dielectric. Okay, so in the perfect conductor, what happens? There is no electric field present inside the conductor, and the displacement current will be 0. But when we have the perfect dielectric case, so in the perfect dielectric case, because this is non-conducting material is there, so in this case the sigma will be 0. Obviously conductivity is 0. So when the conductivity is 0, so in that case the current will be equal to 0. Conduction current will be 0. Okay, so this is the case of when we have non-conduction happens into it. So in this case, we can calculate the ID. So this was the slide in which we see that VC is equal to V0 cos omega t. So D is the spacing between the plates, and AY is the direction from the higher potential plate to the lower potential plate at T is equal to 0. So this is at initial stage. Okay, so right now we are talking about the between the plates when we have the medium, that is dielectric, perfect dielectric. So in this case the current will be I2D. So this I2D is within between the plates there is a medium, that is a perfect dielectric. Okay, so that is why we are calculating the I2D. So that is equal to del D upon del T ds. Okay, so here we can put this value from the D. Here we can use D is what? we can find D is equal to epsilon into E, right? So E is here, so D we can put in place of D this value, right? Okay, so in this case the current equation will become this much. So it is apparent that the expression for the displacement current in the dielectric is identical to the conduction current in the wire. So these things must be clear to all of you. This is the wire in which the conduction current is here, and we are connecting the plates into it, and here in between the plates we have the ID. So it means the current in the wire and the displacement current into the between the medium, that is similar, right? So the fact that these two are equal ensures that the continuity of the total current flowing through the circuit will be executed in it will the same current is flowing into it. So if the one current is flowing it here, so the same current will pass through here, and the same current will be flow into the between the conductors. So this is the conclusion of this complete discussion which we are talking about the current IC and ID. Okay, so even though the displacement current does not transport free charges, so it nonetheless behaves like a real current, right? So this shows as a real current into between the within the perfect dielectric. So this example shows that the wire as a perfect conductor, whereas the dielectric as a perfect dielectric is also perfect. So in this way, the same current will be flowing between in the wire and between the capacitors or the between the plates. Okay, so this I hope this concept which we have discussed, this must be clear to all of you. The what is the what occurs when we have the conduction current. So this conduction current will be into the wire, and the displacement current, it will be in between the capacitor plates. Okay, so these things must be clear to all of you. So this is one of the example which we can go through it, that the parallel plate capacitor whose area is given, that is 5 centimeters square, and the plate separation of the capacitor is given as the 3 mm. Okay, and the voltage source which is applied 50 sine 10 to the power 3 t applied to its plates. Then calculate the displacement current, and here the permittivity is given as a 2 epsilon naught. So it shows the circuit like that. This is our conductor, and this is connected with the source. Okay, so this is the source which is given here, and what we want the what is the displacement current within which is flowing into the between the perfect dielectric. Okay, and the separation between these two plates are given as the 3 mm. Okay, and the plate surface area for this one is given as the 5 centimeters square. Fine. And the next thing which is given as the epsilon, that is equal to that is 2 epsilon naught. So this is the case which is given, and now the thing which is given to us about the displacement current conditions. Now we can find, if we can find the conduction current, then it will be similar as the displacement current as well. So for that we can use this, that D is equal to epsilon E, where E is V upon D. We are very much aware about that because we know this formula, that V is equal to E dot dl. Okay, so in that we can find the value of E. E will be V upon dl. In general, we can define V upon L is equal to E. So in place of E, so we have the dl or the D. So this is that one. So del D is equal to del D upon del T, and here in place of D we can put the epsilon V upon D. So the expression looks like this one. Okay, so JD we got. Then we require the ID, because the question is to find the displacement current. So that is the simple formula which we have, JD dot S, surface area. JD we found from here, and S is there. So simply this one is nothing but this gives the capacitor, that is epsilon S upon D. So just put all the values all together into this equation, we can find the displacement current. Okay, so IC is also the same as we said. If we want to find the IC, So the value of IC and the value of ID is same, and we have discussed all this concept in our previous lecture, that IC and ID both are same. Okay, so based on that we can find the value of ID, and it shows that the ID value is similar to the IC value. Okay, so this was the concept which we have just gone through about the IC and the ID, what is the difference between these two, and in which case we require to find the IC, and what case we can find the ID. Okay, so I hope this point is clear to all of you. Thank you very much for